Well, hi everyone. My name is Jalal Fouani. I'm a PhD candidate at the University of Trento, and my funding is from the Mediterranean Agronomic Institute of Bari. So today I'll be showing you the outcome of our study on the post-diapause vibrational behavior of Halyomorpha. So as an outline for this presentation, I will briefly introduce Halyomorpha, even though it's quite well known by now. I will also be describing the methodology that was used for this study, and then obviously the results. And in the end, I will review the key findings with you. So without any further ado, Halyomorpha halys is an invasive species that is also known as the brown marmorated sting bug. So I might refer to it as BMSB from now on to the rest of the presentation. It's a polyphagous species as it could feed on more than 100 host plants. It's also native to Eastern Asia. It can overwinter in man-made structures such as houses or depositories. And so it's considered a nuisance pest. Due to its piercing, sucking mouthparts, the resulting feeding damage from its feeding is quite significant. And then the result is non-commerciable products. It can have as many as 2 generations per year in different places, but that also varies from one country to another. When it comes to its vibrational behavior, there are 2 protagonist signals that can be emitted by both sexes. First, let's talk about the signals themselves. Type 1 is a continuous signal at a constant frequency around 80 Hertz, while type 2 is a discontinuous signal with a decreasing frequency, which usually ranges from 80 to 40 Hertz. Even though both sexes are able to produce both types of signals, you can see, however, there are some slight differences, as the female signal 2, which you can see in black, is quite has a higher definition. It's quite more regular compared to the male signal 2, which you can see in the lighter gray behind it. While males, on the other hand, emit significantly longer signal 1s, as you can see the male signal 1s in here compared to the female signal 1 in here. So with that introduction in mind, the main aim of the current study was to examine how the vibrational behavior is established post the dormancy phase. And in fact, the most important keyword of the slide and the presentation, I would say, is the word diapause. Among the other aims, we were interested in investigating the temperature effect on the vibrational communication and the potential differences of calling between males and females. So let's jump in at the methodology that was used. First, as a timeline for the experiment, we collected the insects at later stages of the season when the insects were on the verge of going through dormancy, which was around November. We then made them undergo a forced diapause at 8 degrees Celsius for a period of 7 weeks. And then come February, the diapause phase was broken, and the day afterwards, the data acquisition started. We recorded the insects every 2 to 3 days for a period that lasted for 4 months until the insects eventually died. So the 3 chosen temperatures were 10, 18, and 25 degrees Celsius, which were proven previously in literature to respectively coincide with inactivity, the breaking of diapause, and the peak mating activity. At each temperature, we had 2 cages with 10 females each, and 2 other cages with 10 males each, and 1 cage with 5 males and 5 females together as the control cage. The humidity and the photoperiod were constant. The recordings of all temperatures, at all temperatures, took place at the same day in a randomized order. In fact, the insects were sexed into different cages, as we saw earlier, and we recorded separately, as represented in the current slide, using one laser vibrometer, or in a joint state, as represented in this current slide, using two laser vibrometers. The joining of the cages was done by clipping them together from one side. This way, the cues were transmitted and received among insects, but the copulation would never occur. So to sum up, we recorded them at 3 different temperatures in separate cages, or when joining the cages, and of course, when they were together in the control cage. Regarding the results, and starting with signal 1, at 10 degrees, there was no activity whatsoever, as you can see in yellow. And we will see together that in later slides that this is a recurrent pattern also for the other signal. And this agrees with what is already found in literature. Signal 1 was mainly emitted by males, and therefore MS1 was the predominant signal type when it comes to signal 1, which goes hand in hand in literature. And you can see all of the triangles representing the males. We found a smaller latency time before signaling at 25 degrees, especially when the cages were joined. Also, you can note the smaller amount of data at 25 degrees, and this is due to the insect's short lifespan at this temperature. When it came to signal 2, we found the same pattern of no activity at 10 degrees. You can also notice the round dots that are predominant for this signal type, and therefore FS2 is the main signal produced by females, which goes hand in hand with literature. Again, there was a smaller latency time at 25 degrees before engaging into calling compared to 18 degrees. Also in here, you can notice the small amount of the red data representing the 25 degrees treatment, which is due to the shorter lifespan, similar to what was found with the males. So this suggests the potential relationship between the shorter latency time before calling and the early die-off of insects. Moreover, you can note the higher FS2 calling to your left-hand side when the cages were joined, which was expected, especially because females were found to emit FS2 when they would retrieve the male signal 1 rather than emitting it spontaneously. And in here, I'm talking about literature. However, our interesting finding was the fact that the females started emitting FS2 even when they were in separate cages and not being in the vicinity of the males. This does not agree with what is previously known on the species. And this might be due to the copulation abstinence for a long time. However, we also need to keep in mind that the copulation abstinence is we have to keep in mind also that the females were recorded in a group rather than individually, which was the case of the previous works. Also, the cages were stored within the same climatic chamber at their respective temperature, and so we cannot exclude the pheromones as a reason for this behavior. We did not limit our data exploration at analyzing the signaling only. We went further into examining whether the walking could be correlated with the signaling activity or not. So we found that at 10 degrees, there was a minimal walking activity. Also, there was no difference between males and females when it comes to walking. But we also found that there was a higher walking activity when the cages were joined together, which could suggest that there was a higher searching behavior of insects to locate the signal source of the opposite sex when the cages were joined. When comparing with the control, you can notice the clear difference of activity, which is higher for joined cages, especially when it comes to FS2. So this signal type was predominantly emitted when the cages were joined, which might, compared to the control, which might suggest that there's a barrier effect on the behavior of the MSP, meaning that whenever the females were not able to copulate successfully, they would probably spend much more energy and much more time at signaling to increase their chances of mating. If you remember in the past slides, I mentioned the effect of the shorter latency time to engage in signaling and vibrational signaling on the lifespan. So this was further analyzed by the survival analysis, where we found a lower probability of survival at 25 degrees compared to 18 degrees Celsius. And of course, the lowest probability of death was registered at the lowest temperature, where no vibrational communication was registered. And so this further proves the relationship between the latency time before calling and the early die-off of insects. So as take-home messages of this work, we saw together that temperature is a main factor for the emission of vibrational cues. The overwintered insects were directly active at 24 degrees, which is the temperature that coincides with the peak mating activity, even though they just came out of diapause. We also saw that BMSP was inactive at lower temperatures. FS2 could be emitted spontaneously, but only in extreme situations, such as the unsuccessful copulation for long periods. Also, the searching and calling activity is significantly higher in vicinity of the opposite sex, which is what we saw in the joint cages. And with a more energy for calling emission comes the consequence of a shorter lifespan. I would like to acknowledge my co-authors and colleagues who helped in this work and made it possible. And in the end, if you have any question, I would be happy to receive them.